where my little red stool is. Just a minute. It's not here. Okay, so we've been talking a bit about parity. You may ask why all this emphasis calculating the parities. Well, they're work savers, labour savers. You remember earlier lectures on simple harmonic oscillator and infinite square well and all that kind of thing. We saved ourselves quite a bit of work by knowing the parity properties, the parities of these wave functions. We could only do half the work and then deduce what the solution was to the other half of the problem just using parity type considerations. So, well, for example, just off the top of my head, you may have noticed the polar plots. There's a certain symmetry about them. So these lobes, like these wings that come out in the polar plots, if you calculate one, you can calculate the others quite often using symmetry properties. So it's useful to know the parity properties of these wave functions, of these eigenstates, right? So what are the parity properties? What's the parity of the spherical harmonics themselves? The full-blown spherical harmonics, the product of some function of theta and function of phi, right? Well, now let's see. From previous session, we found the parity. Well, stated, asked you to do it for homework. The parity property of the theta function, the theta part of the spherical harmonic was this, and you might even be able to see it. The parity property for the phi function, the e to the im phi, that was minus 1 to the m. So that's where this comes from. So this is the parity term for the phi part of your spherical harmonic. This is the parity term for the theta part of your spherical harmonic. So to get the parity of the spherical harmonic as a whole, you just multiply these two parity properties. Okay, now L and M are integers, right? We did that from the analysis, solving the eigenequations for angular momentum. Now a little bit of elementary math. Now M ranges over less or equal to, it's greater or equal to minus L and less or equal to plus L, right? So it takes 2L plus 1 possible values. So it can go from minus L plus 1, minus L plus 2, 0, 1, 2, L. Right? So there's 2L plus 1 possible values for M, and they're all integers. So M's an integer, L's an integer. Okay, so we can simplify this. So say M is a negative number, right? So this is negative, and we're minusing the mod. So effectively we'll get minus 2m. Minus 2m. We'll make n positive. So that'll be so you got minus 2m as power of minus 1. Well, that's just plus 1. Right? So you just left with minus 1 to the L. Okay? That's when m's negative. Now when m is positive, you'll get minus m plus m, so 0. So minus 1 to power 0 is just plus 1. Okay? So again, you're just left with minus 1 to the L. So that's the parity of your spherical harmonics. Okay? The product of these two, plus a normalization constant, which we did in the previous session. Okay? So knowing the parity properties, that helps you make the polar plots. So polar plots, remember, you take your spherical harmonics, take the absolute values and square them, and the phi term will drop out because the phi appears in the exponential, like e to the I m phi, if you can see it, this kind of thing. So when you're taking the absolute value of e to the I something is just 1. Right? So you're just effectively left with theta. So then you can plot the size of this depending on the angle. And knowing the parity properties, you can save yourself quite a bit of work. Alright? Okay, so moving on a bit. Now we can talk a bit about how the values of m, the eigenvalue m, relate to the eigenvalues little l. Now, a bit of a refresher. What are these? What are the m and the l's? Now, you may remember quite a few sessions back when we were solving the eigenequations for L squared and LZ. Originally we had here just lambda, and we didn't know what it was, and here we had what was it, mu, I think, right? So we solved the equations, and we found that lambda was quantized. Right? It had this form where L are integers. Okay. So that means the angular momentum squared comes in discrete values, sort of like energy in quantum mechanics. So the angular momentum also is quantized. Right? Quantized mechanics, quantum mechanics. This basic notion of this weird kind of mechanics at the very tiny scales. Okay? So you can just see here the allowed eigenvalues for the square of the momentum, absolute momentum, is integer. It takes integer form. So it's discrete. It's not continuous. It's discrete and quantized. Right? Of this form. Now, similarly for the z component of the angular momentum, the component of the momentum L, if you like, relative to the z-axis, it'd be at some angle theta relative to that axis, and that component, if you like, has discrete allowed values, quantized values. M, well actually mh, strictly speaking, the allowed angular momentum is there's an h bar squared term in there, so it's L into L plus 1 h bar squared. They are the allowed the square of the